And so we're very glad to have Raffael Stenzel today talking about proof relevance in higher topos theory. So you can start when you're ready, Raffael.
Yeah, thanks. Let's see if it works. Yes. All right, cool. Okay, thanks for coming. As you see before you, I did not manage to live up to the spirit of the times and acquire a tablet to be able to take notes live and everything. So what you will get is a classic Beamer talk with a semi-coherent Blackboard interface. And whenever there will be a question asked, rather vague hand waving and good resolution though. What I want to talk about today the title sounds like there might be some syntax, some syntactic musings involved in this, but there will be not at all. It's rather a motivation that you will see throughout the talk to do certain things or look at certain things in a specific way. So the why I started looking at this is that I was sometime last year I was just struck by the definition of Groningen topologies as they are defined for infinity presheaf categories, right? Which is basically the same way as they are defined for ordinary topos. And them being defined to be monomorphisms has a very inherent proof irrelevant aspect to it. And I was wondering that if we drop this assumption, how much can we develop, and is this the right way to go? And in the meantime, there have been some papers published related to these issues. First and foremost around Anel, Biedermann, Finster, and Joyal. They had a series of papers revolving around notions in that spirit. And so recently I have worked out some of the stuff, and what I'm basically trying to do is see if looking through this lens makes certain oddities in high topos theory less odd. So there are some circumstances in high topos theory which are commonly referred to as very odd, and I will refer to them during the talk and see if we can resolve those. So this will be largely a soft talk by giving definitions that have been given, giving new definitions, and relating them to each other, and seeing if they explain certain things better. So first of all, we will start with a short motivation. I stole a pun here by Anel and Joyal, which is the topology as the duality between topology and logic. And having done those motivations, I will first talk a little bit about ordinary topos theory and define classic notions in a slightly different way in order to generalize them accordingly in the higher topos context. Then I will introduce the necessary infinity topos theoretical notions that we need in order to get around. And then indeed take those notions we have defined in section 2 for ordinary toposes and define them in the higher topos context. And we will introduce something that I call the logical structure sheaf. It sounds more fancy than it is. You will see it's a pretty basic notion. And then motivate through those a definition of generalized topologies and relate them to what are called lex modulators, a notion that has been introduced by Anel and Lina Subramanian earlier this year, or last year, earlier last year. Then I will suggest how to define, in terms of these topologies, proof-relevant cryptographical semantics, which just suggests itself in this context. And then I will get very hand-wavy because this is stuff I'm looking at right now, and I don't feel very safe about it. So I will just sketch out some outlook in order to give a potential application of what we have been talking about today. All right, so First of all, the motivation. So Johnson has given this very famous metaphor of topos theory as an elephant. And really, in this metaphor, we can think of a topos theory as a Sasquatch, which is basically also pretty big, but much more elusive, at least from today's point of view. So we will focus not on the whole thing as a whole. Indeed, it has often, especially if you look into Uri's book, it is taken mostly from a topological standpoint because he wants to develop geometry and topology in this context. So we will focus on the logical features that we're interested in. And indeed, it has been shown in the last years through various works that every infinity Grothendieck topos has an internal language, which is a univalent type theory. Now, in a univalent type theory, well, we have a notion of predicates, and predicates here are what is usually called inherently proof relevant. So I will not make this precise, but the idea is that if you think of first order logic and you have a set, then a predicate on that set is a monomorphism over that set, right? It basically picks for every element x in x a decision procedure, which says the predicate holds for this element or it doesn't, right? So we can think of the predicate being fibered over that set or that object. And for every x, we have px, which says yes or no, right? It's a 0 or 1. Now, in a proof relevant context, these fibers can be non-trivial, right? They can be as complex as it gets. And indeed, I mean, I write fibered here. So indeed, you can present an infinity Grothendieck topos by a model category, and there are these type families or these predicates are indeed modeled by fibration. Now, there's a very crucial example, namely the identity itself, right? So the identity of an object is a predicate, right? And it can be presented by a fibration of the following form. It's fibered over pairs of elements of X. And for every pair of element X and Y, we have a proof that X and Y are equal, all right? Whatever that means. And so this whole idea of thinking of propositions as types has been captured by this slogan, which is often propagated in the type theory community. All right, so if we think of, so in mathematics, especially in one category theory, we have that duality between topology and logic. So if we assume this duality to be somehow a universal principle, and the logic that we practice here in this context is proof relevant, then its topology should be as well, right? So we will therefore just look at the logic itself and forget the topo part. Now, what we will do is we start with the small category C, and I will claim that there is a certain C index logical structure, which I will call the structure sheet of C, whose ideals in a way, or the infinity toposes embedded in the preshift category, so that the infinity toposes embedded in the preshift over C correspond to the logical quotients or dually the topological ideals of this structure sheet. And if we look at it that way, then in order to capture all such ideals, right, then we should be able to quotient out all suitable multiplicative substructures. So if we take not enough of those substructures, we don't get all the ideals we might be interested in, right? So to make this a little bit more concrete, look at the following. So in ordinary topos theory, we know that if we start with a presheaf topos and we want to get a certain a certain topos embedded in that, then it suffices to quotient out Lorviatian topologies, right? Or equivalently, Grothendieck topologies. Now, Grothendieck topology is in some sense a multiplicative substructure of the frame of all subobjects. And concretely, these objects are sieves, right? So usually a Grothendieck topology is given as a collection of sieves such that certain properties hold. Now, a sieve can be presented as a presheaf. So a sieve over an object C can be presented as a presheaf into the subobject classifier in sets, right? So in some sense, the sieve takes an arrow and then it sends it well, probably the other way around, in fact. It sends it to 0 if f is an S and 1 otherwise. I think I did it wrong here. But anyway, it looks like a classic decision procedure, right? And depending on the definition of S, this also looks very classic, like it might involve the log through the middle or something. So a sieve is in some sense a C-index classic predicate, right? Now, if we know that the internal language of spaces instead of sets is proof relevant, right? It's also univariant type theory, then maybe this is not the natural thing to do, right? Maybe we should look at instead at such predicates which send an error f, not to a simple decision procedure like up here, but really just take all the structure, don't forget anything. So we send it to the space of all elements in S such that S proves that F is contained in S, right? And we have an identity type here, and this could basically be any homotopy type. So there are no restrictions on what the space can look like. So instead of having factoring a pre-sheaf into set through the sub-object classifier here, we can't factor it through anything. We just have to look at all pre-sheafs over the slice. All right. So in order to introduce a few notions that I want to generalize later, let's look at the ordinary case first. So if we are given an ordinary small category, we can look at the following structure. We start in C, and for every object C, we assign to it the slice over C in a covariant way. So a map between objects is sent to the push forward along that map. And then given a category, we can look at the sub-object classifier, which is a category itself, and look at maps into it. And this will always give us a frame. So a frame is a post-level category with all co-limits and finite limits, which distribute well. And so if you look what this function does, it takes takes an object C and sends it to the sieves over the slice, right? So here I'm a bit not so in fact what it does, it sends it. So if you think of a sieve as a sub-object of the representable of C, then it sends it to isoclasses of these monomorphisms, right? And I will call this the first order logical structure sheaf on C. So the notation is obviously borrowed from algebraic geometry, and indeed there are certain analogies, right? So if we think of if we replace the sub-object classifier omega by the reals or the complex numbers, then the whole thing starts. Then the frames by rings. Then the whole thing looks like indeed the structure sheaf over a topological or a ring space. All right. So indeed, this we can think of this structure sheaf as a certain logical equipment, and I use equipment in a not in the formal sense, because if C happens to have finite products, then OC is what is known to be a first-order hyperdoctrine in the sense of Lauvier with equality. So this just means that it satisfies the Beck-Chevalier condition with certain squares in C. So we can, even if it doesn't have finite products, we will think of this thing as a logical structure that we put on top of C, and it's canonical with respect to the to whatever we consider the category C to live in. In this case, it is set. So we make the following definition. It looks a bit of an overkill to define it that way, but this is the way I will define the corresponding notion later on. So if C is a small category, we can define a sheaf of first order OC ideals as follows. So we have OC is a pre-sheaf here from C up to frames, and then we can consider a lift into arrows in frames. And so every JC is an arrow of frames, and we require this to be a nucleus, which is just the classic notation for a Lex modality, left exact modality of frames, or you can think of it as just basically an endomorphism on this frame here, which preserves meets, is monotonous and idempotent, right? So we want for every object C, we want such a nucleus, and second, every arrow is sent to a square of frames, and we want that the induced arrow between these nuclei is just a restriction of the arrow we had before, which was given basically that pullback of monomorphism. And that is all. So I will justify the notation or the term I gave it in a second. Namely, first of all, a sheaf E of OC ideals is literally a subpresheaf of exponential ideals, meaning OCC is a frame, and these ECs here live in there. They are subframes, and sorry, they're sublocales. They're quotient frames, and they're exponential ideals in the sense that is defined in Johnson's book on stone spaces, for example. Yes, and second, why are they interesting? Well, by construction, if you look at what we just defined, it is just a coherent family of closure operators on these frames, right? So this frame is basically just subobjects on the representables, and we have basically defined a closure operation. So sheaf of OC ideals is exactly a Lobationier topology on the presheaps. And how do we assign a Groningen topology to this thing, right? We know there's one-to-one correspondence, and in this phrasing, the Groningen topology consists exactly of those, say, predicates which are nullified in our quotient. So at an object C, it consists exactly of those monomorphisms which are sent to the top element in our quotient frame. Okay, so let's just keep that in the back of our mind for later. Right. So why did I call this a sheaf in the first place? I mean, first of all, it sounds catchy, right? Second of all, it is in fact a sheaf in the following sense. It is a sheaf over itself. If we start with a small category and we have a sheaf of OC ideals as defined before, we can assign to it a Groningen topology, as I just explained. And then this presheaf here is a J stack of frames. So that means that for every J cover, the associated sheaf sequence is an equalizer of frames, right? So, I mean, a priori, I said sheaf and I didn't really specify towards which topology. And in this case, it turns out, well, it's exactly a sheaf toward, yeah, with respect to the topology it defines on its own. So just a word, I will give a quick proof sketch of this. I don't know, it sounds, I don't even know any reference for this. If anybody knows a reference for this, I was surprised not to find anything. But for future reference, so what does it mean that this sheaf sequence is an equalizer, right? If we look at what we have here, it is this product here is indexed over the elements of the presheaf S, right? And this product here is indexed over the arrows in the category of elements of the presheaf S. So the whole equalizer is the description as an equalizer of products of the limit of the functor E restricted to the category of elements of S. So another way to phrase this, that this is a sheaf, is that if we have a site Cj, then a presheaf X is a J sheaf, or in this case, a J stack in this particular setting. If and only if for all covering sieves, the induced map from XC into the weighted limit is an isomorphism. So the weighted limit in this case can be just computed exactly as the limit I have just orally described. So it is the limit of this functor restricted to the category of elements of S projected down to C. So just to give you a quick idea, why is this proposition true? So we want to compute the equalizer, right, of this parallel pair. So what does this equalizer consist of? So first of all, the elements, the tuples in here, consist of monomorphisms over representables, right? And the representables come with canonical maps into S. This is the way we defined it. Now, these monomorphisms are exactly the closed monomorphisms or the relative J sheaves. And a tuple is contained in the equalizer if and only if for every monomorphism in one component and an arrow into that component, the mono in the other tuple is obtained by pullback. So in the end, the equalizer exists exactly of the monic Cartesian natural transformations over elements of S. So yes. So we have this functor here, right? We have this is the category of elements of S, and over each such element in the image, we have given a monomorphism which is closed. And to be in the equalizer means we have this monic natural transformation we are given is Cartesian. Now, if we take co-limits, both on the bottom and on the top, we obtain one single monomorphism over S, which is again closed. And there's a notion of descent for one toposis, which holds for monomorphisms. So descent generally is wrong for one toposis, but there's a notion of monic descent, which is in some sense a notion of descent restricted to monomorphisms, which you can find in Resk's notes on model toposis. And so we see that the equalizer is in fact isomorphic to just single closed monomorphisms over S. And then we can push forward these single closed monomorphisms over S along this covering monomorphism. And vice versa, if we are given a closed monomorphism of the representable, we can push it, we can pull it back. And this push forward and this pull back give us an adjoint isomorphism between exactly what we wanted. So between E evaluated at C and the equalizer of this parallel pair, right? So this is yeah, the sketch of why this sheet sequence is an equalizer diagram. Right. So this is all I want to say about the one topos case, and we'll now look at the higher topos case and see what we can generalize in an according fashion. So I will first make a few definitions. So first of all, I will tell you what an infinity topos is, right? So the most fundamental definition that is often given is the following: that an infinity topos is an infinity category which can be obtained by accessible left exact localization of a pre-sheaf infinity topos, right? So if we think of the one topos case, we know that every one topos is the reflective left exact localization of a pre-sheaf topos. So the only thing different here really is we replaced reflective by accessible. Now by the joint functor theorem, accessible implies reflective. Only in the infinity topos case, the other direction is not necessarily true. Yes. So this is why the accessible why the accessible is there. Now there are different definitions that have been given in the literature. So there are according Giro axioms to characterize infinity toposes, and Raska has given that notion of descent. So an infinity topos is equivalently a locally presentable infinity category which satisfies this notion of descent. Now in the ordinary case, we have a further characterization as those categories of sheaves with respect to a certain site. Now, the way that sites are usually defined, this is considered not to be true in this case. So there are many infinity toposes which are at least not known whether they arise as the localization at a Grothendieck topology. So there is a certain discrepancy. It at least appears that it may be not the right notion to capture all infinity toposes. So instead of looking at these monic notions arising from Grothendieck topologies, there have been certain other notions been studied in order to capture all left exact accessible localizations of the pre-sheaf infinity topos. And such notions have first been considered in the syntactic type theoretic setting by Rieke, Spitters, and Schulman, and then have been considered in the higher topos theory setting by Anel, Biedermann, Finster, and Joyal. And the first definition I want to give here is the following. So we are given an infinity topos, and we want to localize it at something to get a new infinity topos, right? So we can think of wanting to divide out an equivalence relation somehow. We have an equivalence relation in E, and we want to find the right definition of an equivalence relation so that if we divide that out, we again obtain an infinity topos. So in this case, the right notion of equivalence relation is that of congruence, defined as follows. It is a class of maps, L and E, which is closed under certain operations. So it's closed under isos and compositions, it's closed under co-limits and under finite limits. And that's it. Now, we had that accessible part in the definition of infinity toposes. And so also here there is a notion of small generation, namely congruences of small generation, if it is generated by a set of maps instead. And generated here means as a strongly saturated set. So we have to close it under co-limits and the 2 for 3 property. Equivalently, that means that if we localize E at S, then we obtain a notion of S equivalence, which is all the maps which are inverted in the according localization, and we want that L is exactly that class of S equivalences. Now, every congruence can be promoted to what is called a left exact modality. So instead of just having a class L, we can, because it is, in our case, small generated, it will generate a factorization system by just taking the right orthogonal maps and then the left orthogonal maps correspondingly. And generally, a factorization system is called a modality if the left class is pullback stable, and it is a left exact modality if it is furthermore closed under all finite limits. So this means it is pullback stable, and also the fibers over a particular object are also closed under finite limits. And again, we have here a notion of smallness. So a factorization system is of small generation if this factorization system is generated by a small set, in the sense that the left class is the saturation of a small set. And here saturation means closure under composition and co-limits. So how are these things all related? Why did I give these definitions? So there's a proposition, or I suppose, well, I didn't call it a theorem because it's not, I didn't find it stated this way anywhere, but it's just a combination of results of the Anel Bida Majorel Finster paper, Anel Lina Subramanian paper, and results in Louis' book. So if we have an infinity topos, then all these three structures then a one-to-one correspondence to another. So we can take an equivalence class of accessible left exact localization. So these are the infinity toposes embedded in E. Or we can take a congruence of small generation, which is basically this class of maps we had to localize that in order to obtain that infinity topos. Or we can promote that to a left exact modality. And all these things give us the same structure. Right. So this is the first part of definitions I want to give, and I think of them as global structures in the category of pre-sheaf over C. Right. It doesn't really have anything to do with C itself. It has to do with the pre-sheaf over C. A second batch of definitions I want to give in order to generalize that notion of a logical structure sheaf is the following. So we have a notion of infinity topos, and then of course there's a notion of the large infinity or super large infinity category of infinity toposes and geometric morphisms between them. Right, a geometric morphism by definition is a adjoint pair where the left adjoint is left exact and co-continuous, and the geometric direction is the direction of the right adjoint. So we will denote this category by R top, and L top is its opposite. So it consists of infinity toposes as objects, and the morphisms are the left exact co-continuous functors, right? Which exhibit the right adjoint accordingly. So such a geometric morphism is called an embedding if the right adjoint is fully faithful, right? So in the geometric morphism, in the geometric direction, we have an embedding basically. Another definition that will be of interest of us is the notion of an étale geometric morphism. So an étale geometric morphism is one that is up to equivalence simply the left adjoint is given by this canonical map from E into one of its slices, right? They're often thought of as the local homeomorphisms among geometric morphisms. So it can be quite hard to figure out whether or not a certain geometric morphism is étale or not, right? So there is nevertheless a category, again, where we can restrict the category of infinity toposes to the one with étale geometric morphisms between them, and then again consider the opposite to those. Now, what does it mean how can I find out if a certain geometric morphism is étale? Well, there is a recognition theorem, which has been proven in the infinity context, again by Lurie in the book. And it turns out that a geometric morphism can be seen to be étale, so equivalent to such a functor into the slice, if and only if this left adjoint part admits a further left adjoint, which is conservative, and satisfies a certain generalization of the Beck-Chevalier condition, which is often called the projection formula or the push-pull formula. I will not get into the details of what it means, but yeah, you see it here. It's a certain distributivity between the left and the right adjoint and pullbacks. All right, so why did I give you these definitions? So let's try to do what we did in the ordinary context in the infinity categorical context. So we start with a small infinity category C, and then as before, we can look at something as before. So we embed C into its pre-sheaves, and then we take the full slice. Before, we took the sub-objects over representable. Now we take all objects over representable, right? And here we go into the category of all infinity categories. So what are the values of this thing, right? So up to equivalence, every value is just pre-sheafed over the slice. There's a natural equivalence between these things. And pre-sheaf over the slice is again the same thing as a right fibration over the slice. So the way I think about it is before we were looking at those right fibrations which are -1 truncated, basically. So they are monomorphisms over the slice. And we thought of them as predicates, right, in the classical sense. Now here, a predicate can be any sort of right fibration where we think of a predicate P sitting over the slice C, and the points in there are the proofs that that predicate is true. Again, we have obviously induced transition maps between the values here, but these are not just some functors, but we in fact know that they are geometric morphisms, and in fact étale geometric morphisms, because we have a push forward and we have a dependent product. So in fact, this functor here factors through the category of infinity toposes and étale geometric morphisms between them. And once again, I will refer to this pre-sheaf here as the logical structure sheaf and justify the term later. So as before, we can look at ideals of this thing. So I gave you the definition of congruences and left exact modalities in a global setting, right? Sitting in the pre-sheaf category over C. And now we can do the same thing indexed over C locally. So I give you the following 3 definitions. First of all, a congruence of small generation on this logical structure sheet will be just a family of congruences in these infinity toposes, right? So this is just pre-sheafs over the slice. And we know what here congruence of small generation is. And we want that this family is in some sense coherent. So we can move from one to the other, right? So there are certain certain transfer properties we want to have. So the pullback of the congruence over D lies in the congruence over C, and so forth. Same thing with left exact modalities. We could say that the left exact modalities of small generation over C is again a family on these pre-sheaf categories, such that they translate to one another in the very same way. And third, I make the definition of what it means to be sheaf of OC ideals, and it is basically the same thing as in the ordinary case when we replace frames by infinity toposes. So a sheaf of OC ideals is a lift of the structure sheaf, and obviously evaluated any object. This is, well, a left exact co-continuous map, right, between infinity toposes. And we require that this is an embedding. So before we had a nucleus, now we want this to be an embedding of infinity toposes. And what do we want for the maps to hold? Well, every map becomes a homotopy commutative square between infinity toposes. And we have assumed that these guys here are embeddings, right? The horizontal maps are embeddings. And we want the vertical maps to be, first of all, we know that this guy here is étal, and we want that this map here is étal again. And secondly, we know that this square from the right to the left commutes, by definition, basically. And we want also that the square commutes in the other direction, so that these maps are really just the restrictions of these maps. All right, so in some sense, we have squares of infinity toposes, which are horizontally embeddings, and vertically étal maps. So this looks maybe on first sight rather random, but we have the following way to transfer between these structures. So given a small infinity category, then to give such a C-indexed congruence on OC is the same as to give a left exact modality of small generation, again on OC, which is the same as to give a sheaf of OC ideals. So this is basically the same proposition we had before in the global case, but now in the local C-indexed sense. And indeed, if our category that we started with has a terminal object, then of course, OC of 1 is just all pre-sheafed on C, and the value of E at 1 of such a sheaf of OC ideals will be just a left exact localization of the pre-sheaf infinity topos. And it turns out that this is the left exact localization associated to E in the following sense of the theorem, namely, we can relate the C-indexed local notions with the global notions we had before in the following way. If we start with a small infinity category C, then to give a global left exact modality on pre-sheaves is the same as to give a C-indexed local left exact modality on this structure sheet. So as a corollary, we obtain that to give a sheaf of OC ideals is the same as to give an equivalence of accessible left exact localizations of C, just as in the ordinary case. So in the ordinary case, we said that a Grotny topology consists exactly of those predicates which are nullified, right, in that ideal that we are considering. So we can make the same we can look at the same thing here. So if we start with a sheaf of OC ideals, then we can look at all the maps of a representable which are contracted locally in that localization. And it would be sensible to consider these things as generalized topologies, right? So one could wonder if we axiommatize them abstractly, if we get a one-to-one correspondence again between such abstractly axiomatized generalized topologies and well, sheets of OC ideals or infinity toposes embedded in pre-sheets over C. So before I go into no, actually, yeah. So first of all, we can give such a definition, but it's very unattractive, to be fair, and I'm a bit unhappy with it. But I found nothing easier than that. So we can make a definition of a generalized topology, namely, as before, it is a collection of now not monomorphisms but general morphisms, which satisfy certain closure properties. So this ought to be unital, it's ought to be stable. So if we have a covering map over a representable and pull it back over a map in C, then it's ought to be a covering map again. And third, it's supposed to be transitive in the following sense. If we have a map that is covering and we have a map into the domain, which is locally covering, so for every pullback of that map into a representable, that pullback is again a covering map, then we want the composition to be covering as well. So these three axioms are exactly the three axioms we know from ordinary Grothendieck topologies when we restrict to the case of monomorphisms. But if we don't restrict to monomorphisms, this is not enough to capture the structure that we need. We have to get more. Namely, fourth, we have to require that these collections over given representables are left exact. So if I have a finite diagram of covering maps over the same object, I want that the limit is again a covering map. And then I want certain co-completeness conditions. So fifth, I want that the maps which are locally covering maps of a YC is supposed to be close on the co-limits. I just gave that some name. Local co-completeness seemed to be a self-evident name for this. And sixth, we want this again to be generated by a small set in some way, right? We had all this small generation in all our definitions, and here again we will have a notion of small generation, and this is also not very elegant. So we want that our Grothendieck topology J is generated by a small set B, basically, if we read this here, by a transfinite iteration of the plus construction, right? So we know that sheafification generally is computed by a iteration of the plus construction, and we can just be more vague here in the definition and expect that every element in J is obtained by some transfinite composition of co-limits of elements in B. All right, so this is the definition of a generalized topology, which is a mouthful, especially a mouthful to check if you want to check whether something is a generalized topology, which I will get into a second. First, though, we can prove that the thing that we wanted in the beginning. So if we start with a small infinity category, then there is a bijection between, again, the accessible left exact localizations of C hat and generalized topologies on C. So this basically saves the day for the notion of a topology in order to capture all the structure we want. And secondly, why did now I have I have a way to say what a sheaf is, right? I always said we have a sheaf of our C ideals, but what actually is a sheaf if I don't have a notion of topology to be a sheaf for? So now that we have a notion of topology, I can justify the notion of sheaf of our C ideals by the following proposition. If we have an infinity category C and we have a generalized topology on it, then we have an associated sheaf of our C ideals, which is such a pre-sheaf into infinity toposes. And this turns out to be a J stack or a J sheaf again. So in the following sense, which I have alluded to earlier, namely, for every cover, for every map over the representables, which is contained in J, the induced map from the value at C into the weighted limit is an equivalence, right? So in this sense, those things are sheaves indeed. Indeed, again, sheaves over themselves in a way. All right. This is basically the part of definitions of things I've introduced, and it's a lot of stuff I've introduced, and the aim was to explain how to look at infinity toposes from a certain perspective, and this motivation of looking at proof relevance in this context does suggest a certain proof relevant cryptographical semantics for these generalized topologies. So let's remember what cryptographical semantics is. So if we are given a small infinity category C and we have a map of pre-sheaves, then we can define a model relation of this form. It's often denoted in this way by this forcing thing. And we say that OC models phi, or the truth value of phi in OC, is just the space of lifts along a certain given element, where here the element plays the role of variable. So phi is a map from Z to X. We are given an element from YC to X, and then we look at the space of all lifts from YC to Z over X, right? So in classic cryptographical semantics, we only look at monomorphisms. And given an element of this form, we just ask, is there a section or not? And hence it gives us a truth value, which is again evaluated in the classical subobject classifier of sets, right? It just says yes or no. Here we don't quotient out that information in some sense, because we don't start with a monomorphism, and we don't just ask whether or not there's a section, but we just take the space of all sections, and this will be our space of truth values. Yes. So furthermore, if we are given a sheaf of OC ideals, we can define a corresponding space of truth values for this sheaf E by taking again the space of lifts, but not into the pullback along X itself, but we first pull back and then we map down into E, right? We basically take the closure. We look at lifts into the closure of the map we started with. Now, if the map between pre-sheaves happens to be a map between sheaves, then it is the same thing. So the space of truth values with respect to our structure sheaf is just equivalent to the space of truth values with respect to the sheaf of ideals, because the closure of such a relative sheaf is just the thing itself. So I only looked at this notion rather superficially. So it kind of suggests itself, and I don't really know how far you can get with this. I don't really know where you can take this. So what you can do for sure is prove a theorem which takes certain type formers or certain categorical constructions in your infinity topos and send it to the corresponding categorical constructions in spaces, right? So we have such a theorem in the one topos case, and we have such a theorem here as well. So if we start with a sheaf of OC ideals, and we have an associated generalized topology and a J sheaf, then we have the following translations. The truth value of the empty statement is basically the empty space. The truth value of the trivial statement is the trivial space, right? These are kind of obvious. Then you can do the same for products, for coproducts. So the truth value of a disjunction of maps is just the disjunction of truth values. And you can go on to sigma types in a way. So if you have a composition of two maps between J sheaves, then the truth value of the composition is the space of witnesses that that E models at phi, together with a witness that E models the pullback of psi evaluated as. So in a way, we have this space of truth values of psi over phi, and this is it comes naturally with a map into the truth values of phi by push forward with psi, and this can be understood as the total space of this map with fibers given exactly by these truth values. A similar thing holds for pi types. The truth value of a dependent product of two maps is, in some sense, again, proof relevant for all statement. So the index I have written here is a bit sloppily notated, but it in some sense says for for every generalized element of C and for every witness that the statement is true restricted to that element, then we want also to have a witness of psi, right? So yeah, we had a witness of phi restricted, and then we also want to have a restricted witness of psi. And same thing for equality. So the truth value of the equalizer of two sections to a given map is the path space between the 2 points, which are elements of this truth value itself. So it's all rather straightforward. Just for the pi types, you really have to use first of all a Beck-Chevalier condition for sigma and pi, and for sigma and pullback in the infinity topos, in the infinity presheaf topos, which follows the projection formula of Italian geometric morphisms. And you want that J sheaves are closed under dependent products, which basically follows from left exactness of the localization. All right, so yeah, in the last 5 minutes, I just want to quickly go into examples or what you can do with the things I have just looked at or defined over the last 50 minutes. So we have seen that the definition of generalized topologies is pretty much structured. Like it doesn't look like you could give easy examples of those. But just as in the ordinary case, usually you don't give a Grothendieck topology directly, but you give a basis for the Grothendieck topology. Now there's a similar notion in this case, which turns out to be the notion studied by Anel and Lina Subramanian. Namely, they have defined a notion of modulator. So they first given a presheaf category, they define a pre-modulator to be just some collection of maps of representables which contains the identities, right? So every MC should contain the identity. That is a pre-modulator, pretty easy notion. A pre-modulator is a modulator if it is pullback stable. So the important thing here is this is not a collection of classes, but it's a collection of sets. And pullback stable in this case means if I have a map in MC and I have a map from D to C and C, then the pullback or any pullback along this map is equivalent to some map in this modulator. And then a modulator is left exact or Lex, they call it the Lex modulator, if all these fibers here are co-filtered. So it's a relaxed notion on left exact. So we could just as well ask for the existence of all finite limits, but it suffices to just have cones. They are not necessarily limiting cones. And it turns out that we can think of these Lex modulators as bases for generalized topologies. So we have required that a generalized topology is generated by set B, and by the closure properties of a generalized topology, we could have just assumed that B is a Lex modulator in the first place. Secondly, if we have a generating Lex modulator of a generalized topology, then we can compute the localization at J just by looking at M. So the localization at M computes the whole localization at J. Basically because, right, J is generated by co-limits by M, and so the localization will not make a difference. So in particular, the sheafification with respect to such a generalized topology can be computed by the transfinite iteration of a plus construction of M, which has been studied and defined in the same paper by Anel and Lina Subramanian. And third, if we start with a Lex modulator, then we know that the localization of this thing is left exact, and so it will give a unique generalized topology. So after all, it's enough to just give a Lex modulator in order to generate a generalized topology and hence a left exact localization of presheaves. So how do classic Grothendieck topologies fit into this picture? Well, remember that a classic Grothendieck topology is a family of collections of monomorphisms which satisfy the first three conditions of those 6 I gave for generalized topology. Now, a classic Grothendieck topology is generally not a generalized topology because it fails to satisfy the co-completeness condition. The problem is basically that not even monomorphisms do satisfy this co-completeness conditions. We just fly out of monomorphisms. But it is always a left exact modulator. It's always a left modulator. So if we start with the Grothendieck topology J, then we already know that it always generates a left exact localization, which are exactly the topological localizations, and hence it generates a generalized topology, a unique one associated to this guy. But the definition of a generalized topology is not that far away yet from that of a classic Grothendieck topology. The reason is if we restrict to the monic context, so if we ask conditions 1 to 6, so it should be 6 not a 5. If we look at conditions 1 to 6 and we replace everywhere all the relation of J to all maps over YC to J to only the monomorphisms, then it turns out that the conditions 4 to 6 are Becky's. They are always satisfied. Left exactness basically follows from upwards closeness and transitivity, and a similar argument can be made for the other 2 arguments. Yes, so the definition of a classic Grothendieck topology is the same as the one of a generalized topology, just restricted to monomorphisms. And it's already 2 p.m. I will just fly through the rest because the rest is rather it's just motivating anyway. So it's really hard to give examples still. So even though it's enough to give just Lex modulators, one way to give Lex modulators is via just subcategories of your domain C, which contain identities and are closed under compositions and finite limits, right? Because if you look at the image and the Unada embedding, then this is easy to be seen to be a Lex modulator, and hence generates a generalized topology. By definition, something is a sheaf for this if and only if it sends all elements in F, all maps in F to an equivalence. So in particular, a representable is a JS sheaf if and only if it is S local, right? So again, in particular, if we take S to consist of all arrows in C, then the JS sheaves are exactly the homotopically constant pre-sheaves on C. So one might think that, well, maybe we can use this to give proof-relevant versions of certain interesting Grothendieck topologies in the classical case. Take the regular topologies in a regular category, or the coherent topology, or the extensive topologies and things like that. But it's unfortunately not that straightforward. So for example, if we look at what we would like to be the proof-relevant regular topology, and we take a category C, which has enough structure to define what an effective epimorphism is, and so that the notion of an effective epimorphism is pullback stable and such things, then we could think of taking just the class of all epimorphisms and just take the Unada embedding of that, right? Instead of -1 truncating everything, we just take the full thing. And instead of asking for a map to have a lift into an effective epimorphism, we really take just the space of all lifts. Instead, we don't divide anything out. But the problem is that E is not left exact. And in particular, the Unada embedding of this guy is, even though it is a modulator, it's not co-filtered, and it's not a left exact modulator. So the localization of this guy will not be an infinity topos. It will be semi-left exact, but it will not be left exact. Yet we can still wonder what the local objects are, right? And here in this case, the representables are sheaves or local for this not topology, if and only if they are right for orthogonal to all effective epis, which means they're -1 truncated themselves in C. So yes, so the question is there maybe if we think of C to be equipped with a certain notion of logic, proof relevant logic, and we want to find what it means to be classifying infinity topos for this proof-relevant logic rather than only the proof-irrelevant -1 truncated fragment. How does the theory of such classifying infinity toposes look like? So something I want to just quickly mention is a theorem that is very important in this context. In the ordinary case, is the linear completeness theorem, which states that if we start with a coherent topology, coherent category, and we take its classifying topos, which is a coherent topos, then it always has enough points. So this is a way to state a Gödel completeness result in this categorical context. Now, Lurie has shown that if we just generalize this in some sense, let's say naively, then it fails. So there is a coherent spatial locale, there's a coherent topological space, whose infinity topos of space valued sheaves does not have enough points. So in some sense, the completeness theorem fails. But here sheaves means really they are pre-sheaves which are local with respect to a certain Brody topology. And maybe this is not the right thing to consider. So a suspicion or question here is if it's really the completeness theorem that fails, or if it's just a miscommunication between certain -1 truncations we are taking here and logical structure that we should not -1 truncate. So what one might look at is instead not -1 truncate and look at certain generalized topologies obtained by looking at certain finite limits obtained in C. So for instance, we have this modulator, which is given by just take any finite diagram in C and take the co-limit in C if it exists, and then just take the formal co-limit of the representables over C, right? And this is always a modulator, and the pre-sheaves which are local for these guys are exactly the limit preserving pre-sheaves. So the pre-sheaves which take a co-limit in C and send them to a limit diagram in spaces. And maybe we should take a fragment of those guys in order to obtain a correct or a good notion of classifying finite toposes, which maybe even does satisfy Gödel completeness. And this is where I wanted to get to. Thanks.
Okay, thanks very much for a nice talk, Raphael. So we have our round of applause, and then if anyone has a comment or a question, go ahead and ask.
Can I ask a question?
Of course.
Raphael, when you say classifying topos, like classifying topos of what? And this is a serious question, because do you mean a type theory, or do you mean a theory in a first order logic or a variation of it? Because yes, it seems to, oh, sorry.
I would think here of a type theory.
Okay, I agree. Okay, that was because I think something like in first order logic cannot work in a sense. It must be some type theory. Okay.
Exactly. And I don't know exactly what that would look like, but it would be an interesting thing to study.
But did you think about these representable categories by Uemura, or just maybe how do you call natural models by Audi?
Well, I have looked at natural models, but not in this context. I would have. So I did not see a connection to this. So I did not look at it in connection to this.
Because in principle, a natural model should be a dependent type theory.
Yes.
And so one can say, okay, let's try to, for each one of those, to associate to it a classifying infinity topos. So take this as a notion of theory.
Yeah. Oh, yes, correct. Yeah. Makes sense. Yeah.
Thanks.
Yeah.
Any more comments or questions? Well, if not, then let's thank Raphael again. Thanks for that, Raphael.
Yeah, thank you. I've been rambling a lot, I suppose. It's been the first time I've been talking about this like at all. And so it's quite, it was a bit all over the place. I apologize.
It's interesting. And okay, so there will be no talk next week. And then on the 10th of June, we have Noam Zeilberger. So that should be maybe connected to theoretical computer science. Okay, so that's it for today. We can stop recording.